Thank you for the kind introduction. Hey guys, I hope you guys had your coffee, you're awake. This is something that I say before almost every talk I give. I'd like this to be a dialogue and not a monologue. So if you have questions, if you think what I'm saying is right, wrong, please speak up. That'll make for a more interesting session rather than me droning on for about 30 minutes about what we have been doing for the last several years. So with that, let me get into the talk. So as was presented by the previous speaker, collectives are actually pretty important. Why? Because if you look at end scientific applications, they use collectives, and most of the time that is spent by applications is in running various MPI collective operations. So if you take like P3D-FFT or PSDNS, they are kind of extremely communication intensive. They spend about 45% of the overall application execution time in communication. So that's at one extreme. But if you look at typical scientific applications, you would see that they'll be spending around 10 to 20 or maybe about 30% of their time in communication. And this keeps increasing as the scale of your job increases. So if you don't have collectives that are designed well to scale well inside a node as well as outside of a node, then your application performance is going to get significantly impacted. Now in this talk, what we'll be presenting, or what I'll be presenting, is the work that we've been doing in our group over the last several years to address these challenges. So how can you scale collective operations for dense many-core nodes, and how can you ensure that they scale out to the large supercomputing systems like Astra and Stampede 2 or the upcoming TAG Frontera system. So what are the problems with existing collective operations? So in this slide, we try to elucidate that. So the top black line presents the theoretical peak bandwidth that you can get on a given system. And what we have shown in this slide is the amount that various collective algorithms are able to achieve, like the amount of peak bandwidth that the various collective algorithms are able to achieve. So here we have taken the example of all-to-all because that's a very dense communication intensive collective operation. So as you can see, some of the most popular algorithms we have are not able to saturate your theoretical peak. So this is where, and this is especially true for the dense many-core nodes like your Skylake or ARM kind of systems. So this kind of forms our motivation. So what can we do to ensure that the performance of collectives kind of comes closer to this theoretical peak from where it is now? So we can see that there is about 3.5 like factor of 3.5 difference between what the best algorithm can do right now and what the theoretical peak is. So what we are trying to do is, can we try to fill this gap and get the performance to where we want it to be? So we have done this work in the context of the MVAPICH2 MPI library, which is a pretty popular MPI stack like on the lines of Intel MPI or OpenMPI. So we've been around for quite a while, and we have different, let's say, flavors available depending on the kind of hardware configuration you have. So if you have GPUs, or if you have your like dense many-core nodes, or if you are running on the cloud. So depending on the kind of hardware platform or infrastructure you're running on, we have different versions available. And we are also a partner in the upcoming TAG Frontera system, which will be the fastest supercomputer in the US in an academic setting. So what are the directions that we are focusing on in MVAPICH2 as far as accelerating collective performance goes? So we do several things, but due to lack of time, in this talk we'll be focusing on 4 particular aspects. So one is, can you take advantage of kernel-based communication schemes like Linux cross-memory? So how many of you here know what Linux cross-memory attaches, CMA? Okay, at least the MPI folks do know that. So if you look at a single node, 2 processes running on that node, how can those 2 processes talk to each other? So one way is obviously through the network. So you use some sort of a network loopback for communication. The other popular method is to use shared memory-based communication. So process 1 and process 2 establish a common shared memory pool. Process 1 puts the data in the shared memory pool. Process 2 copies the data from the shared memory pool to its buffer. Okay. So if you look at it, there are multiple copies involved here, from the user space buffer to the shared memory buffer, the shared memory buffer back to the user space buffer. So this is the typical way your, let's say, intra-node shared memory transfers work. But there are more transfers here than we would like. So people tend to use, like most high-performance MPI libraries, use what is called as kernel-based mechanisms to reduce this two-copy approach to a single-copy approach. So basically, in the kernel-based copy mechanisms, you would map the source buffer directly to a kernel region and copy the data through the kernel from the application's source buffer to the target application's destination buffer. So you, in a sense, have reduced the two-copy scheme to a single-copy scheme. So this is the primary advantage of your kernel-based transfer mechanisms, and this is very popular. But what is the problem of such kernel-based transfer mechanisms? For instance, the CMA or cross-memory attached feature from Linux is one such popular method which is available by default in the Linux kernel. So if you look at it, point-to-point is fine. But when you go one step further, when the density of communication increases, when you go from point-to-point to collectives, the story completely changes. So in this slide, we are trying to present that story. How does your collective communication get impacted by your bottlenecks in the Linux kernel? So if different processes are talking to each other, like something like a point-to-point, you see that there is no increase in your communication latency as the density of communication increases. So point-to-point is fine. But how about a typical collective operation like a one-to-all or like an all-to-one? So as you can see, for a one-to-all kind of an operation, there is a significant degradation in your communication performance as the number of communicating pairs increases. So if you compare one pair versus 64 processes communicating with each other, there is a significant degradation in your communication performance for a one-to-all or an all-to-one kind of a pattern. So why is this so? So this is what we try to analyze in our lab. And we have tried to come up with optimized solutions to see how this can be tackled. So when we try to analyze the cause for this degradation performance, we saw that it was because of the contention for getting a lock. So if you look at how CMA works, it calls a function called getUserPages, which calls a page level lock in the kernel. Now this page level lock scales very poorly as the number of processes trying to get the lock increases. So that is why if you have a collective communication pattern where multiple processes are either trying to send to one process or trying to get one from process, which is very typical in collective operations, your communication latency significantly jumps up. So what we are trying to do is, can we try to come up with algorithms, stage them properly so that the access patterns are much more cleanly regulated, okay? So this goes back to what Brian was saying earlier. Typical MPI algorithms does not do any back pressure. It does not care about what the network or what the underlying communication mechanism is capable of doing. It just keeps on pushing, assuming that the underlying communication, let's say hardware, it could be shared memory or your network, is capable of handling whatever you can throw at it, which is not really the case. So here what we try to do is we try to schedule the algorithms in such a way that the communication does not cause contention inside the node. So creating such contention aware algorithms by creating such contention aware algorithms, we were able to significantly improve the performance of your communication operations for single node as well as multi-node. So again, if you just create some great mechanisms for one node, that is not good enough, because your typical supercomputers are comprised of hundreds of thousands of nodes. So you need to ensure that the intranode communication mechanism you create plays well with the internode component and is able to deliver performance at scale. So single node is important, two node is important, so is 10,000 nodes. So what we try to do is we try to create efficient two-level algorithms. So you have one kind of communication scheme for intranode, another kind of communication scheme for internode, and we try to make them play well with each other. Now, unfortunately, these numbers are for KNL, and most of us know that KNL is dead. But what I would like you to take away from this slide is that even though KNL is gone, you have other dense many-core architectures like Skylake or Cascade Lake, ARM coming up, and the same kind of fundamental like locking issues in the Linux kernel would be applicable to them as well. So these designs are going to be very valuable for the emerging dense many-core architectures. So this is one of the things that we try to do to improve the performance of your collective communication primitives for the upcoming dense many-core era. So I think the previous talk talked about Sharp. So this is kind of taking that. So I mentioned that you could design two-level or multi-level algorithms with Sharp as well. So why do you need multi-level algorithms? So if every process on the node tries to join what is called as a Sharp, let's say, group, then you hit kind of a scalability issue in the switch. There is a limit as to the number of processes that can join a particular Sharp group. Okay? So if all the processes on a node blindly join the Sharp group, then you will not be able to use Sharp beyond maybe a couple of hundred processes or a couple of thousand processes. So what we tried to do was we tried to create efficient multi-level algorithms for Sharp which are aware of your intra-node process layout. So if you look at it, your typical HPC node has multiple sockets, and each socket would be at a particular distance away from your network interconnect. And most of us know that in order to get the best kind of performance, the process which is doing the internode communication should be physically close to the HCA. So here what we tried to do was we tried to have a NUMA-aware design, as in we would, instead of having one leader process per node to do internode communication, you would have multiple leader processes to perform the internode communication. And you could have 2, 4, or 8, whatever number of leaders that you want. So you would have these leaders performing an intranode operation, and then they would work with each other to finalize the internode operation using the underlying Sharp mechanism that the Mellanox hardware exposes. So with this, we were able to show pretty good scalability at the microbenchmark level for an already used application, as well as at the application level. This is an example of the HPCG application using the proposed designs. So what I would like you to take away from this slide is that you can do Sharp in a very naive way, but if you do it like that, you will probably not get the best kind of scalability. So you need to be very careful about your intranode process layout. You need to be NUMA aware. And if you have such NUMA aware designs, you get much better performance than what a naive solution can offer. And this can have significant impact as you scale up. So because of lack of access, we could only run this on 16 nodes. But if you scale this up to maybe 1,000 nodes or 2,000 nodes, the impact would be much, much better. So typically what we have seen is that hardware offloaded collectives perform much better than your host-based collectives because you don't have to go up and down the stack. So there is a significant improvement in performance at the micro benchmark level as well as at the application level. Now, one other benefit of hardware offloaded collectives is basically to implement non-blocking collective operations. So how many of you are aware of this concept of non-blocking collectives? Okay. So if you look at collectives, there are two general kinds. Blocking collective, where the communication library is in the operation and actively progressing the communication. There is another sort of collective operation which is called non-blocking collectives, where the idea is this. The MPI runtime or the application would kick off a collective operation. Then the theory is that there will be some entity in the background to progress this collective. What this entity is not very clearly defined. It could be the application process itself. It could be an additional thread. It could be a hardware engine. Now, obviously, if you have a hardware engine, this could be in the HCA or in the network, progressing this collective, then you get much better offload. So that's what we are trying to highlight here. So if you take a non-blocking reduction, like an I already use, and try to implement that or design that using Sharp, then you get significant overlap of computation and communication. So if you look at a scientific application, its main job is compute. It needs to do science. Communication is like a necessary evil that it has to do in order to scale out. So if you can completely hide the cost of communication, then that is best for overall application performance. And that is where this concept of non-blocking collectives and the concept of overlapping computation and communication comes in. So if you can use the features that your high performance network provides in an efficient way, you can achieve this kind of performance and get much better improvements at the application level. So this was for the host side. So how about the GPUs? So GPUs need a different kind of a design because the communication paths are completely separate and the performance equations are also different. So what we try to do is we take a holistic approach and try to take a look at different critical collective communication operations for GPU-based clusters. Now, if you look at the current state of the art, GPUs are most commonly related with deep learning. And if you look at deep learning, reduction is the most critical communication intensive operation that deep learning application uses. So we took the MPI all reduce primitive and tried to see if we can improve the performance of the all reduce primitive inside MVAPICH2 GDR compared to NVIDIA's Nickel and Nickel 2 solutions. So Nickel is fantastic at what it does. And what it does is very, very large message reductions. It does not care about your small message or medium message reductions. Okay? It does this very, very well. But one thing that people typically don't realize is that deep learning applications is not all about very, very large message reductions. There are different kind of communication operations in like a deep learning framework like TensorFlow, where you have some small message reductions and some medium message reductions happening as well. So if you just use something like Nickel or Nickel 2, which is purely geared towards your large message end, you might not get the best possible performance for your deep learning application. But MPI has been doing reductions for 20 years. So we know that if you take a ring algorithm, that is not probably going to give the best performance for small messages. So we know that if you want to do, let's say, a good performing reduction operation for small to medium messages, you'll probably have to do recursive doubling. So we utilize our knowledge in designing collective communication algorithms. We pick the right sort of algorithms for the right message sizes, and we are able to deliver this kind of performance benefit. So if you don't use the right algorithms, as Nickel and Nickel 2 is doing, you get significant degradation in your communication operation. So that's what we are trying to highlight in this slide. So that is at the microbenchmark level, but nobody really cares about microbenchmarks. What is the impact on like an end application? So here we took TensorFlow, and this is the Horovod implementation. So do you guys know Horovod? Okay, a few. So how many of you have heard of TensorFlow? Okay, a fair number. So TensorFlow is a very, very, very popular deep learning framework. It's being used extensively in the community. And Horovod is a contribution to TensorFlow by Uber, which allows TensorFlow to use MPI for the reduction operations. So we use that with MVAPICH2 GDR and also with Nickel 2, and we are able to show that even at the application level, using MVAPICH2 GDR is able to deliver the much better performance than using Horovod over Nickel 2 or Horovod over an unoptimized version of the MPI runtime. So again, going back, what I would like to stress on is that yes, Nickel 2 is fantastic, but there are a lot more things that Nickel 2 doesn't do, which is required for your deep learning applications to scale. So that is where our proposed solutions come into play. So this is the same solution for like a different model called ResNet 50, and we are able to show significantly better performance when you compare to the Nickel 2.3 solutions. Yes. Sorry, I don't think I have the ideal scaling here. Yes. Sure. So the question was that what percentage of this performance is to the ideal? So I don't have those numbers here, but I can take it up with you often. We have that in the paper. I can mention that. Any other questions? Okay. So going forward, this is the last portion that we have. So typically, if you look at intranode communication, as I mentioned, It happens through explicit communication. So let's say if I want to do a reduction of 2 buffers, I get the data from process 1, do a reduction, and then send the data back to like different processes. So this is typically how it happens. You have an explicit copy of remote data to your local buffer. But you have solutions like XPMM and others which enable you to have load store access to a remote process memory once you have registered it. So what we tried to do was, can you use this technology of XPMM and perform reductions directly on the remote process buffer? So the critical difference is that if you look at your CMA operations, there is still one copy that happens from your remote process buffer to your local buffer. That cannot be avoided because you don't have the ability to directly touch that process memory. But with XPMM, you have this ability. So think of like a reduction implemented using XPMM. So you can register the local process memory, the remote process memory, and you can do A plus B. So there is no actual additional movement of like copying of data that happens from A to B. So you can avoid that. So that is one of the significant, let's say, differences your shared address space mechanisms enabled by technologies like XPMM brings in. So one of the that is one benefit. The other major benefit of XPMM based approaches is that if you look at CMA, you have this locking overhead that comes. You have to do like process VM read V or process VM write V, and that calls a get user pages call where there is a lock. But with XPMM, there are no contention overheads. So if you want to implement very, very dense collective communication operations for your emerging many core era, this is kind of the way to go forward. So we have tried to design various collective operations using the XPMM interface, and I'll show those slides in a bit. But first, we would like to show some numbers from like mini applications like mini AMR. This is on the HPC side, and Microsoft's cognitive toolkit, or also known as CNTK, representing the CPU-based deep learning. So as you can see, you get significant performance benefits if you use the proposed XPMM-based shared address space mechanisms to perform your collective operations. So in this slide, both of these applications were using the already-used primitive, but it is not just that we have done already-used. We have also implemented XPMM-based broadcast. So you get significant performance benefits over solutions which don't have the ability to use such like shared address based mechanisms. And these solutions will be available in future releases of MVAPICH2. So typically this is what we do. We do research, we publish a paper, and once that is published, we try to take that into the code, do test, and release it so that the broader community can take advantage of whatever research that we are doing. So this is the performance of like a broadcast. So we have implemented XPMM or shared address based collectives for various collective operations like broadcast, scatter, and gather, and also for all-to-all. So as you can see, for all of these different collective communication primitives, you get significant benefits for your shared address space based mechanisms. So I think I have a couple more minutes, so let me try to conclude right now. So what was presented in this talk so far? So we shown how communication mechanisms and runtimes need to be redesigned to take advantage of the high concurrency being presented by the emerging many core architectures. We also presented a set of novel designs for collective communication primitives that addresses several of these challenges, both intra-node and inter-node for modern clusters. We also demonstrated that there are significant performance benefits to be gained by applying these techniques in a judicious fashion based on your use case. So before I go, like I just come here and give the talks, but these are done by a lot of graduate students who work tirelessly back in our lab, and I'd like to publicly acknowledge their effort in getting all of these designs done, published, and made available to the user community. So that's my talk. Thank you. So I think I have any questions? Okay, thank you. Oh, sure, yes.
So what is exactly
Sorry?
So you only, so where do you get XPMM from?
So Nathan Helm hosts it on GitHub. So we get it from that. So XPMM as a product is kind of stable right now. So it has been, I think the last time Nathan made a commit to it was several years ago. He just migrated it from GitHub to GitLab some time back. But like XPMM as a module is extremely stable. We have not seen any issues with the module itself. So even if nobody develops XPMM for the foreseeable future, we don't see issues. The only known issue for XPMM is that if you want to register like an XPMM based buffer with IBB regmr, that doesn't work. But that's a bug on the InfiniBand side, and I think Jeff Hammond has a...
No, it's not.
Sorry,
That's
yes.
a bug with XPMM.
Okay.
And XPMM won't work with GPU buffers in the future, and it's just going to become increasingly broken. So
Probably.
It would be really great if someone in this room was interested in stuff would be come forward to maintain it, or get it upstream or something like that.
Sure. So following up on... Do you have time? So following up on Jason's comment, I think Jeff Hammond has a patch to the IB driver which enables that registration to work. So again, maybe we can take that offline.
Yeah, but it's still an XPMM bug.
Probably. Again, I'm not too familiar with that. We can probably take it offline. So yes, the other comment Jason made, if you guys didn't hear, was that XPMM will not work for GPU buffers, but this solution was only meant for host, not GPUs. Yes. Any other questions? Yes. So Limit is, we are kind of trying to deprecate that, because if you look at KNM, Limit, and CMA, there is not much of a difference between any of these solutions, and CMA is available in the Linux kernel, and people like to use that. So if I ask somebody to say that, hey, I have this fantastic kernel module, go install it, the first reaction I get from the sysadmin is no. Kernel module? No, I'm not going to do that. So when you have something in the Linux kernel which comes for free, why like force others to use Limit? Yes?
Do you have any preliminary data on multi-socket Xeons?
All of these were taken on multi-sockets. So all these results that I showed here, these were taken on dual socket Broadwells. So 2 sockets, 14 cores per socket.